For our last sequence of videos, yes, sequence because I'm breaking them into smaller bits, we have our radical chemistry, which is found in chapter 25. This first video is going to try and do the big overarching summary that covers the primary characteristics, and then the subsequent videos will be smaller sections that look at some of the complications and potential side issues or oddities if you wanted to look at those. So, first and foremost, free radicals. These are unpaired electrons. So if I wanted to draw a carbon as a radical, it would just have a single electron. Some of the rules that are going to change with this, as we saw with the sodium Birch reduction, we're moving one electron at a time, which means our curved arrows are going to be what are known as fishhook arrows. Fishhooks because we don't have a double barb, there's just a single barb. So the barbs represent the number of electrons being transferred. Why radicals? Radicals, well, the first and foremost reason of why radicals is that they exist, and that these reactions do happen. Why do they become synthetically useful for organic chemists? Is that their primary target is the alkane functional group. The alkane functional group that has virtually no reactivity. Because it has so limited reactivity, we need to do something, radical to get it to react. Hence, we've got our radicals. So, their stability of radicals can very closely be approximated to carbocations. So, you can apply your understanding of carbocations to radicals. Except rearrangements, don't do that. And the next part is because radicals are so incredibly reactive that they tend to react with the most available electrons. Okay, and that will become relevant as we kind of move through, depending on our reagent conditions. That preference for available electrons increases in some cases, or decreases and reaches normal levels. So, free radicals are unpaired electrons. What I've got showing on the right are some examples where these could potentially come from, and we'll see these reagents pop up, would be something along these lines. This compound would be a decent starting material to throw in there, and that oxygen-oxygen bond is incredibly weak and can split as a free radical, and so the molecule would split apart. Oxygen itself is technically a diradical, okay, or can be a diradical, and it's part of that chemistry, or part of that reason is why oxygen is so incredibly reactive as a gas. There's also some other spin states associated with it, which you don't need to worry about, that also limit some of that reactivity, which is why we can exist, because we can tweak it between those chemistries. The other big common radical you'll see is the bromine radical, and then you'll see carbon radicals. So within that, we now have some examples of radicals, so let's go through and start looking at the breakdown of the reactions. Like I said, we're doing single electron motions, which means their mechanisms are a little bit weird and hinky. Ultimately, what we can do is we can break down their mechanisms into different stages of a reaction. So that first stage would be the radical cleavage, okay, or the radical initiation, and this is done through a homolytic bond cleavage. Most of our mechanisms, for instance, if we start at that peroxy compound, would be a heterolytic. All of the electrons go one direction. That's heterolytic. And that works out great when we're talking about electronegativity and stability of charges and all that fun stuff, okay? And large differences in electronegativity. Because those things are typically common, we see those a lot. For radicals, these things happen because we have to have a balance of electronegativity, and it has to have something else to help contribute and weaken that. So you're typically looking at very electronegative elements being bonded to each other. So in the case of the oxygen-oxygen, what we're saying is one of those oxygens takes one electron, and then the other oxygen takes the other electron. And so what we're getting is a hetero or homolytic bond cleavage. that bond is easy enough to break with heat. The result is we end up with two radical species. Those species are now what are going to initiate and run effectively the rest of the reaction in those particular cases. If we go through and look at BR2, BR2 is an extra interesting case, and we'll see why in a little bit, and I'll allude to it here in a second. Same deal, it can do homolytic cleavage. That bond is a little bit stronger, so it needs a little bit stronger energy signature, and we're looking at light. It's usually kind of deep UV. Don't quote me on that. I'm pretty sure it's UV. And again, we're going to be forming that radical species. Once it's initiated, those radicals can now go off and try and stabilize by effectively sharing their one electron with something else that then causes that to cascade out into other things. Okay, and that would be our subsequent steps. I remember where I was going. Remember BR2 we've also used as an electrophile, and when we used it as an electrophile, we were talking about a heterolytic bond cleavage. So BR2 is a tricky molecule because it can act under heterolytic conditions and homolytic conditions. So what's really going to drive bromine's chemistry is being very careful to really look at the conditions, the reaction conditions that you're under. If you see light, you need to be going radical mechanisms. If you don't see anything extra, so we'll just say nothing extra, then you should go as bromine as an electrophile. Okay, so that's a subtle line that you need to walk. So our radical initiation, to say it again, as our big summary before we move on, our radical initiation is the formation of a radical. So we start with no radical and then we become radical. After that, we're now moving into our actual reactions, and this would be our propagation. So propagation is that radical reacting with anything it can come in contact with. So for instance, if we go through and look at that very first one, that bromine can share a single electron. Now, what is it going to share that single electron with? Okay, the highest probability that it's going to share things with are going to be hydrogens. Okay, and you might ask, why hydrogens? Well, the reason why we would be going with hydrogens is because hydrogens are on the outside of a molecule. Those are the most likely things to interact with a radical. It's going to be hard to react inside the molecule unless there's something, say, reactive like a radical in it. Okay? So in our propagation, we could go through and run that reaction. The result, though, is I'm also going to need a single arrow going there. That's going to result in that blue radical, where I now have the radical on that last carbon. I could just as easily as an OR, and since I don't want to do it as an OR, I'm going to erase all this. I could just as easily have also gone through and said that radical could have shared its one electron with the hydrogen that's further substituted in there. The result is that I would end with the green radical. Okay, so there are two possible radicals that could form for this particular substrate, for just a propane. We get two possibilities. Both of those reactions would technically be, or not even technically, they would be propagation reactions. Because they can both form, we now have to decide, should they both form? And a lot of that should is going to come in as a complication further on down the road. For right now, what's useful to remember is that with bromine, because it's a useful radical initiator, it will go through and form the most stable radical possible. Because we said radicals roughly equate to cations, the green one is more stable and more likely to form. The blue one is less stable and less likely to form. Right? And again, in the subsequent video, we'll see more on that. Once those radicals have formed, those radicals now get to float through solution and potentially react. The next most likely thing for them to encounter would be more bromine in this particular case. Okay, and again, we'll talk about that a little bit later. So we could get the radical reaction, where we've now gone through, and if we consider beginning to end what happened, we've done a substitution, hydrogen for bromine. So one of the big kind of characteristics for our radical mechanisms, our radical reactions, is that we are doing a substitution. We are not doing it as a nucleophile substitution, we're doing it as a radical substitution. And so what we're exchanging is hydrogen for bromine. So no leaving groups, nothing like that. We're just forming our radicals, just as simple as that. But we're doing hydrogens for bromines. That was sarcasm. And before you start being like, well, all these other things that could stack into it, it's literally just hydrogen for bromine. We're talking about our radical reactions, at least at this stage, you're just doing hydrogen for bromine. That's it. That's all you do. Okay? What happens in the blue case? The blue scenario, which we said was unlikely to form, okay? And what we're saying by that is that that radical is so unstable that it would very likely just react back with the HBr, and we don't see any product formation, okay? But what I'm attempting to show here is that we could theoretically also do the other, that was horribly drawn, the other substitution where we have the bromine at the terminal position. Okay, very commonly that bromine is going to go internal because of the stability of our radical. Okay, so cool. That's our propagation reaction. We started with a radical, there's a radical, and we end with a radical. Okay, each of our propagations is doing the same thing. In the course of this particular reaction, if we added bromine to the alkane, we would form the radical on our bromine, we would propagate to form the radical on our carbon, we would then propagate again to put the bromine, do the bromine official substitution, which then still gives us a radical, which can then continue to run the reaction. Okay, so one of the things that makes radicals kind of interesting is that they are kind of self-sustaining and they will keep producing more radicals. This is also one of the reasons why free radicals in our body can become dangerous, because as they react, they continue to make reactive radicals. Okay, so that's one of the things just to be aware of with our radicals. Eventually, we need to stop these radicals from reacting, though, and that's where we encounter our termination. So the termination is now the loss of a radical. These terminations happen, just like the initiations, happen very infrequently. Okay, the initiations are very small concentrations. You're forming very reactive species. So the odds that we actually form a radical, even in that initiation, are very low. But once formed, the propagation continues to form radicals, while we could potentially continue to initiate more radicals. So we get kind of an exponential growth, which is unfortunate timing for this. Okay, but we get a lot more growth of those radicals, so the reaction runs. As the concentration of radicals increase, we increase the likelihood, okay, based off of concentrations, that two radicals could impact each other. If they interact with each other, well, now the radical reaction stops. Okay, there's no more radicals there. Okay, so our radical reaction would then be terminated. There's a variety of ways that we could go through and do this. Pretty much any radical process could go through and do this. One of the things I do want you to note is that if you look carefully, and I don't remember which color-coded I use, we can end in this termination with the exact materials that we ended with in the propagation, which is actually completing our substitution. But in a proper radical mechanism, these steps here are not the likely or the highest probability of finding or making your final product. Okay, because that stops the reaction, that stops making more product. Okay, so we decrease the odds there. The radicals could encounter other radicals as well. It doesn't have to be ones producing product. They could be doing things where two alkane radicals interact with each other, and we get this goofy thing, which would be interesting. And so we would get a lot of potential side products with our radical reactions, particularly as these terminations come into play. It's all driven based off of stabilities. Okay, so we can get lots of bizarre stuff happening in small concentrations. Okay, they're small concentrations because radicals are limited in their formation, because we have to have a photon of light cause the radical to initiate. Then the radical has to continue to form, and then you're effectively having two branches of those radical paths crossing each other. Okay, and that becomes a more challenging thing to have happen. The probability falls off. Nearly everything that we do within radicals is probability based. The last way we could go through and stop a termination or stop a radical reaction is you can throw in what's known as a scavenger. And in fact, it would be a radical scavenger. The radical scavenger will react with radicals because it produces very stable products, and we would throw that in, and that would kind of kill the reaction. Okay, terminate or quench the reaction. Okay, and those are the basic steps of our radical reaction. We have our initiation, our propagation, and our termination. Remember, the majority of the chemistry that's happening to produce products is happening in the propagation steps. The termination and the initiation are really just kind of almost afterthoughts or forethoughts just to get it started. Okay? Yeah, I'm just going to leave it at that. So, the big thing that I think you really need for our radicals is what is the summary. So, what are the big reactions to run? So, this shows all of the reactions that you're expected to know for radicals. Initiation, propagation, and termination are terms and applications that you're supposed to know. So I'll go ahead and handwrite those in right now. So we've got those terms identified, so you should be able to look at a reaction and be able to match that up. And so with that, we've got our basic reactions, we've got our overarching ideas. It's now really just looking at nuances behind this. Okay, so with that, I'm going to run into the next video.